The use of fruit peel powders in functional food formulation reflects a strategic integration of nutritional enhancement, food sustainability, and product innovation. The hypothesis that fruit peel fortification boosts the fiber, antioxidant, and micronutrient content of everyday foods without negatively impacting sensory appeal is not only plausible but increasingly validated by early research. These applications span bakery items, breakfast cereals, extruded snacks, and even dairy alternatives. When properly formulated, such products can deliver meaningful amounts of polyphenol, vitamins, and dietary fiber, while also valorizing waste streams from fruit processing industries. Fruit peels are naturally dense in bioactive compounds that concentrate in outer tissues due to their protective function. Apple peels, for instance, are rich in quercetin, catechins, and insoluble fiber. Mango peels concentrate S-carotene, gallic acid, and mangifrin. Banana peels offer resistant starch, potassium, and serotonin precursors, and beet peels carry betalains with potent antioxidant activity. When processed into fine powders, typically via drying and milling, these peels can be stably incorporated into flours and dry mixes without requiring refrigeration or preservatives. This creates an ideal format for scalable fortification in low-moisture food systems like crackers, granola bars, or instant porridges. Nutritional enhancement is substantial even at modest inclusion levels. For example, studies have shown that substituting 5% to 10% of wheat flour with apple peel powder in muffins or breads can increase total polyphenol by 40% and fiber by 20%, with only minor changes in color or texture. Similar effects have been reported using carrot, orange, and pomegranate peels. A particularly well-documented case involves mango peel. A 5% substitution in cookies or cereal bars elevates antioxidant capacity, vitamin A precursors, and dietary fiber, while also reducing postprandial glycemic response. This latter effect is thought to stem from peel fiber's ability to delay starch digestion and flatten blood glucose peaks. Sensory acceptance is a key concern, but not necessarily a limiting one. Most peel powders impart subtle earthy, fruity, or bitter notes depending on the fruit source and drying method. Consumer studies suggest that peel-enhanced products are acceptable up to 5% to 7% inclusion, especially when paired with complementary flavors or sweeteners. For example, banana peel flour in pancakes or muffins adds a mild nutty flavor when used at low concentrations, while apple or citrus peels lend aroma and moisture retention. Beet peel may darken color or introduce a faint bitterness, but can be masked with cocoa, spice, or molasses. These findings emphasize the importance of pre-treating peels, e.g. blanching, fermentation, or enzyme hydrolysis, to improve palatability and reduce astringency. From a food science perspective, peel powders influence not only nutrition but also functional properties such as water absorption, bulk density, and emulsion stability. In bakery applications, they can reduce staling and improve moisture retention due to high fiber content. In extruded snacks, they act as crisping agents while reducing glycemic load. In meat analogs or dairy substitutes, peel fibers can serve as binding and gelling agents, replacing synthetic thickeners or gums. Pilot-scale studies have already explored this. For instance, carrot peel powder added to muffins increases total dietary fiber by over 30%, while preserving acceptable texture and flavor profiles. Banana peel flour has been used in cookies and pasta to enhance fiber and potassium, with optimized formulations masking color changes. Guava or kiwi peel flour has been studied for gluten-free applications, leveraging their high vitamin C content and fiber-binding capacity to stabilize crumb structure in non-wheat breads. A major research direction is standardized comparative analysis, evaluating different peel powders, apple, mango, citrus, banana, grape, across identical food matrices to quantify their effect on total polyphenol content, antioxidant activity, via DPPH, FRAP, vitamin C or E levels, beta-carotene, and dietary fiber. Ideally, these would be paired with consumer panels rating taste, texture, aroma, and appearance. Experimental arms could include both untreated and pretreated peels, as well as whole versus defatted powder versions, to assess trade-offs between nutrition and sensory quality. Beyond the lab, small feeding trials could investigate metabolic effects such as satiety via fullness ratings or ghrelin assays, glycemic index via glucose curves, and microbiome impact via fecal SCFA or fiber fermentation markers. These would offer preliminary evidence for the functional health claims of peel-enhanced products, supporting their classification as functional foods. Importantly, this approach also aligns with sustainability principles. Fruit peels make up a large portion of food processing waste, especially from juice, drying, and canning operations. Turning this biomass into a stable, nutritionally potent ingredient reduces landfill burden, cuts greenhouse gas emissions, and creates a circular economy value chain. For smallholder farmers and food processors, this valorization pathway could open new markets and revenue streams. In summary, incorporating fruit peel powders into functional foods is a viable and increasingly evidence-based strategy to improve nutrition, enhance food functionality, and reduce waste. When formulated thoughtfully, such products can meet clean label demands while delivering real health benefits, positioning fruit peels as a valuable frontier in next-generation food innovation.